Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming, and to all our viewers online. It is my pleasure to welcome Hridesh Rajan from Iowa State University. Hridesh has been there since 2005, and prior to that, he was at the University of Virginia, where he worked with Kevin Sullivan and got his PhD. His primary area of research has been on aspect-oriented software development, and he's actually going to talk to us today about a new project he's been working on called BOA, which is about mining large-scale software repositories.
Well, thank you, Nachi, and thanks for coming both here and online. So this talk is about BOA, which grew out of my personal pain trying to do empirical evaluation of programming languages in some sense. This is a joint work with Robert Dyer, Hoan, Nguyen, and Tien, Nguyen. All of them are at Iowa State University. So hopefully I don't have to convince many of you that mining software repositories is an important aspect of software development analytics. I mean, we want to be able to learn from the past to perhaps spot anti-patterns, what is actually practiced, and then help those observations to inform the future. So for example, to find better designs, keep doing what works, do some empirical validation. So there are, so in order to mine software repositories, the first thing often is to find a target repositories to mine. So there are several examples of repositories that academics have access to, and then some organization-specific repositories that industry folks have access to. This is a rich set of data that is available out there, and it's valuable in the sense that it allows us to make observations that previously would not be imagined. So to give you an idea of the scale of these things, there are three large repositories: Google Code, GitHub, and SourceForge. And these three together have over 1 million projects, over a billion lines of code, and tens of millions of revisions of things. When you compare this to a large software company, this is really not such big data. But for academics, this is a huge amount of data that is available at our disposal to be able to test research hypotheses. So what would be examples of such hypotheses? I picked some simple ones. So for example, you could ask, what is the most used programming language? A very simple hypothesis. How many methods in my code are named tests? What is the number of unit tests in the system? You could ask things like, how many words are in log messages? Do people actually bother to communicate their intent when committing code? You could ask questions like, how many issue reports have duplicates? And this is essentially a very common question in software development. So I'm going to pick one of these questions and explain to you what it takes to answer this question today. So here's this task. And this task is computing what is the average churn rate for Java projects on SourceForge. Churn rate is essentially the average number of files that are changed per revision. Okay. So today, if we wanted to go and do this task, we'll first go to sourceforge.net, and we'll say, OK, let me mine the project metadata. This is essentially a JSON file. And then for each project that you find, you're going to run this loop. Okay. And what this loop does, it essentially says, OK, is this project a Java project? Sure, if that is the case. Then does it have a repository? Is that the case? If so, then write some code that accesses a repository to mine revisions, and then using the revisions calculate project rate and keep churn rate, and keep doing this until you're done to finally give you the average churn rate of the project. Now, for somebody whose primary task is not mining software repositories, this is a lot of work. So a solution I present on the slide there. It's too much code. Don't bother reading this. It just we just wanted to illustrate it to show how complex it could become. So this code is written by a mining software repository expert, who is one of my collaborators. So it's really optimized. It's down to the bare minimum. So over 70 lines of code that you have to write, and you have to write this code after you know about these two libraries, JSON libraries and SVN libraries, and how to access them and use them effectively. This code runs sequentially, and it takes over 24 hours to run and process SourceForge data. So if you start running it, it will take over 24 hours. And if you take the time to download the project data locally and run this code on that download data, it will take almost 3 hours to run and finish this code. Now, it is conceivable that one can write a parallel version of this, which will run faster. But that will be additional complexity on top of what we have already for answering a relatively simple question. Here is an alternative in BAW. This program essentially answers the same question. I'm going to explain different parts of this program to you as during my presentation. But just to make some basic high-level observations, this full program is about 6 lines of code. It doesn't require users to understand external libraries. It's automatically parallelized, and it gives you the same result in about a minute. And that's what BAW is all about. Okay? It's about giving software engineers and programming language practitioners capabilities to write queries of this sort and be able to run them in a timely manner in some sense. Okay. So this is the topic of my talk: BAW language and data-intensive infrastructure. It is available with limited release right now at baw.cs.iowastate.edu. So to tell you a little bit about how I came to BAW, from 2005 and to 2012, the focus of my work was reconciling modular reasoning and separation of cross-cutting concern. I worked on a language called Ptolemy with Professor Gary Levins from University of Central Florida that had this whose primary goal was to do this. And as part of language evaluation, we wanted to empirically validate Ptolemy's design. We want to say, okay, we wanted to use real code and a significant set at that to show benefits. And the questions that we wanted to ask are which projects use event-based separation of concern, and how do they evolve over time. Okay. So to do this work, I had a couple of my students look at and mine software repositories such as SourceForge and so on. It took them about 3 months with not very much significant result coming out of that. I didn't think much of that problem at the moment, but when recently again, when I started working on this idea called modulation-guided parallelism in this programming language Panini that we are working on. I'm not going to get into the details of what this does, but we also wanted to do the same thing here: empirically validate what does the design looks like. Wanted to use real code and significance that show benefits, and for that we wanted to find out which projects use concurrent programming language feature. And the same story, so 3-4 months of time that students spend, not so much progress to show for it, because it's just very hard to do these things manually. So a lot of work, not so much result, and so then we sat down and thought about, oh, can we fix this problem? Can we fix the problem of doing these sort of queries so that we can get these results in a reasonable time and not have to write thousands of lines of code or spend thousands of hours doing this work? And that's where BAW came to be. So BAW has 3 design goals. First one is that it should be easy to use. It is for folks, and I will come and explain to that. The second is that it should be scalable and efficient. And the third is that it should enable reproducible research results. And I will explain to each of these goals. So easy to use, this should be a simple language. No need to know the details of repository mining and data parallelization. And essentially, what I want to do is I want to be able to empower social scientists and humanities experts to be able to do open source research. That's essentially my goal with this project. There's also a little story behind this. I mean, this requirement came out of a collaboration that I'm recently involved in with an English faculty at Iowa State University. And this person is interested in understanding whether terms may mean the same thing in different domains. So, for example, if I use the word efficiency in one context, does it mean the same in this other context? So this person is trying to do the study for open source research, and he came to me and said, this is just too hard to do this sort of work. As a person who doesn't know very much about programming and details of that, it's just not possible for me to go and answer these sort of questions. And BOA is hoping that we will fill this sort of gap, and I will come back and show you some details on that. Another goal is to be scalable and efficient. We want to study millions of projects, and we want to have results in minutes and not days. And essentially, what we want to do is we want to have a more ambitious, data-intensive scientific discovery in this particular area. Finally, we want to have reproducible research results, and this goal essentially came out of this paper that was published in a conference called "Mining Software Repositories" by Gregory Robles. This paper essentially studied results in this area, about 171 papers and it essentially says that only about a couple of them were replication friendly. And it's for a variety of reasons. Sometimes the data source is not available. It's proprietary data source. So I mean, there's really nothing that authors can do to make this. But we wanted to fix this problem as well, so that researchers can provide something that a third party can verify on, and we'll show how we achieve that. And if you have any questions, please do not hesitate in interrupting me. So BOA capabilities essentially are on 3 dimensions. First dimension that most program analysis folks are familiar with is containment. So we look at a program as an abstract syntax tree. Programs contain classes contains methods contain statements, and so on and so forth. And when we think about program analysis, we think about this containment relation. Okay, so that's one dimension. The second dimension that is important is software artifact evolution. In the sense, how does code change over time? Is the method being added? Are the statements being added, and so on? The third dimension that is of interest to us is scale. We want to be able to do this on a very, very large source code base. And I'm going to now delve into the details of this language. So let's look at the BOA architecture. An important component of that is this data store that we have. Data store essentially replicates SourceForge. There is some caching translation goes on, and essentially creates a local cache here. It essentially keeps it up to date in some sense. That's the responsibility of that. Other aspect of that was designing the language. The language that we are designing, and I'm going to come to the details of that, essentially a variant of a language that came out of Google called Sawzall. Okay, and we did more work on that. On top of that, we have added domain-specific types and functions, and I'm going to get into details of those also. As part of, we built a compiler for BOA, which because Google's compiler Google's language is available, but the compiler isn't available in a usable form. So we did some work on that. Essentially, a BOA program runs like this. So once you write a query program, it is compiled. A query plan is created. This query plan is deployed in the cluster, which makes use of local cache, which finally produces query results. So this is a standard MapReduce environment. And I will see a demo of that also today. Regarding domain-specific types, this is one of the core contributions of BOA. What kind of types do we need to provide to make job of a mining software repository export easier? So BOA provides certain domain-specific type. In this program, we are seeing several domain-specific types. So project is a type. Project has properties like programming languages, code repositories, repository kind. Code repositories have properties like revisions, and the revisions have properties like files, and all that. Once these facilities are available at the language level, the person is not doing any work to mine these sort of information.
So, sorry, can I think of these types as basically just being the schema of the underlying data?
Yes, you can, and that's at the implementation level. That's where we start from. Okay. So the role that these types play is to abstract the details of how to mine software repositories, so that we people can just worry about program in terms of these. Okay. Yes.
But I mean, maybe you'll explain more of the program later. But I'm confused about the program. If you're going to compute the average churn rate, I would have expected to get a number out. And here the main operator exists. So I would guess from that this turns out that it gives you Boolean.
I will come to that. But yes, you will get a number out. And so for now, think of the first line in the program as what you will get out of it.
The rates?
Yes,
oh.
Yes. And I'll come back and talk about that also. So here's some details of this domain-specific type. It provides the name of the project, homepage, URL, programming languages, licenses, and all that information that you would typically expect from a project. There are other types like code repositories, revisions, files, and so on, and they provide usual details about these artifacts. More information about this is available from the website, of course. We also have domain-specific type for source code analysis, so these include declarations, namespaces, types, etc. Things like variables, things like modifiers, things like methods. So all these types are essentially to make the life of a mining software repository export easier. We also have a statement level access and the expression level access. So you really have the entire abstract syntax tree available at your disposal. Once again, I'm not getting into the details of these because this information is all available online, and really when you're programming, you can look up which type you need. Okay. So both types are not specific to any particular language. It generally cannot support any object-oriented language. Currently, we have support for Java source code, but we are planning to have support for C++ and also for C# if we find a library that is useful. What we do essentially for mapping is we parse the source file, generate AST, and then we store it in the distributed database. And the database that we are using here is the HBase database to do the job here. So Java code like that would probably be represented like this, an internal AST. And again, the details of that are not so important, but just taking a look at the containment relation. And this is essentially what I meant when I talked about the containment dimension. You can browse through the statement and say, and what is the name, what is the variable, what are the expressions that it contains, and so on. This is, to a programming language person, this will come naturally in some sense. This is standard AST containment. We also provide domain-specific functions. These are first-class functions that we make available in the language. So has file type is a function which takes two arguments, revisions and a string, and returns a Boolean. And as the body of that function, it tests whether there exists a project, there exists a file that matches certain format. And if so, it returns true. Otherwise, it returns false. Okay. There are other versions of these functions that take project or code repository. So here's another example. This is one of the common things that people do in mining software repositories to say whether when somebody committed a code where they're fixing a bug. So this function tries to test for that by looking at the log of the commit message, because oftentimes people write things like fixing this bug or fixing some other bug and so on and so forth. So it looks at the log string and it says, okay, if it's matching certain pattern, then we will consider that as a bug fix or not. The details of this particular implementation is not so important. What's important is that a user is allowed to write these heuristics themselves. Okay. So in general, user-defined functions take this form. Return type is optional, and essentially the idea is to allow for some other complex algorithms to be encoded. Next are quantifiers, and this was essentially earlier your question, Rustam. So quantifiers are essentially the same as in mathematics, and this essentially allows us to easily express loop over data, and bounds are inferred from the conditionals. So I'll go through some of quantifiers in detail. So this is one. This is essentially for each quantifier, it says for each value of I, if certain condition holds, then run body with I bound to the value. Okay. The exist quantifier essentially is the same as mathematical exist. One would imagine. If there exists a value of I where condition holds, then run body once when I is bound to one matching value. Okay. And if all essentially says that if for all values, if the condition holds, then run body once with I not bound. So the reason why we have these is because we have found that these kinds of quantifiers make the task of expressing queries easier. Okay. So BOA hides a detail of distributed computation, and underlying architecture is uses a MapReduce framework. So I'm going to, for those who are not familiar with this, I'm going to give you a quick summary. So MapReduce is essentially this idea that you are processing a bunch of data, and in the map step, you process, you have identical copies of a program that each processes a certain portion of the data, and then in this shuffle step, you take the output and you take it to a reducer, which then, based on its output, gives you one or more values. So essentially, this idea is same as there's multiple data, but the single program is running on each data set. Okay. So that's essentially a basic idea. It's not an invention, not the contribution of BOA per se. It's but BOA makes use of that paradigm. So output and aggregation are part of BOA's design. So output is defined in terms of predefined data aggregators like sum, set, mean, maximum, minimum, etc. Values are sent to output aggregate variables. So an example of output is declared here. This says rates is an output, and this rate is going to compute by computing a mean indexed by the string sent to it, and this mean will be essentially an integer. Okay. Here is sending data to the aggregator, and this we are using a C++ syntax of doing if you're familiar with sending data to output, C out or C in, you will probably immediately see what's going on here. So we are sending to rates, and we are not just we are sending rates an index and this value. So it's essentially saying find thing at this index and increment the mean with this additional data value. Okay. So let's see it in demo. See if there is a so when you go to the Voa web page, there is a user login on the left. We don't have open access to this infrastructure available yet. But once you log in, you get to this page. This is how you use Voa, out of a tablet or a smartphone or your web browser. And we teach people how to program in Voa using examples. So we have a wide variety of examples that we make available to users. So if my query matches one of these examples, I'll typically start with that. So imagine for a second that I was interested in saying in asking this question, how many projects use the Java programming language? So I will start with this example, which says how many projects use the Scheme programming language. And this, when I pick that, it populates the program. And here, this program is saying that the output of this program is counts. It's going to be sum of integral values that are sent to it. And input of the program is a project. And for each integer I, such that the programming language used in the project matches scheme, I'm going to send a value 1 to the counts, so that basically counting distributed overall. So I want to change this program to say that counting projects using Java. Okay. Now this is a little program that counts the total amount of projects in SourceForge that use the Java programming language. Next thing we have to do is we have to pick which data set we want this program to run. And this is sort of where the reproducibility requirement comes in. When you report a result, you could report a result by mentioning which data set you ran your program on, so that there is a better understanding to the third person that, this is the data set on which this result holds. So we have only one data set at the moment, which was done in 2012 July. We are planning on doing one more snapshot. But I'm currently just going to run it on the live data. So once I have my program, I can then run it. This is essentially just clicking the button. That's about all the work that a user has to do. So it's going to compile the program, and let me return to the presentation here for a second. So we will wait about a minute for the results. But so let's understand why are we waiting for these results. This program that we just wrote is analyzing about 600,000 projects. It is analyzing about 370,000 repositories and about 4 million revisions. Okay. And these are contained in this many files. Okay. So let's take a look at what the program is doing. So see here, the compilation has finished. It's just the execution has also finished, and this allows you after the execution has finished, it allows you to see the job. It says only about 50,136 projects use Java as a programming language. Okay. You can also download the Java output if you so wish. If let's suppose your program made an error, you can edit the source code and you can send the new query that is based on your earlier program. And this sort of has to do with all of this has to do with the ease of use requirement that I pointed out earlier. We want this to be available to a class of users that just cannot be bothered with installing a bunch of libraries and a bunch of other software system to make their queries work. They should be able to just point to a web page and be done with it in some sense. So this is a requirement that BOA achieves very well in this setting. So we already checked the results of BOA. We checked the performance of BOA on a bunch of tasks. The important details of these tasks are not important. It's essentially different categories of things. More details about that is in our XC paper this year. What we saw is that compared to Java programs, BOA programs achieved results in much faster time, and this is as you can see, this is a time in logarithmic scale. On an average, BOA programs finish much faster. There were three categories of these programs. The one category was of these programs where it was accessing only one revision. The second category was where it was accessing all revisions of a project. And the third category was where it was only doing metadata. That was this guy here. Okay. So Java programs, as you see is variance, but the BOA programs are nearly take the same amount of time. And most of that essentially is Hadoop's startup overhead here.
So the Java programs are sequential, they're not anything parallels.
Java programs are sequential, but they're looking at local, and you can for example parallelize them if you would like.
Okay, but the main speed up here is due to parallelism. I mean, I'm just trying to interpret why.
The main speed up here is because of parallelism and also because of data storage strategies. Those two things play a role, because querying from distributed store versus querying from a centralized data set, that's where it comes from. Yeah. Any other questions on this? Okay. So look at it in some more detail. One of the important things to note is predictability of result. BOA programs nearly, we can say, it takes about a minute. It will take you about a minute to run it. Whereas for a Java program, it sort of varies based on what you're trying to do. Okay. Next thing we did was we examined whether these things scale. So for that, we again looked at three different output categories: 6,000 projects, 60,000 projects, and 620,000 projects. 6,000 projects and 60,000 projects were picked out of this set using random sampling. Okay. And this again shows the BOA programs in blue and Java programs in red. As you can observe, for Java programs, for different data set, the performance, as expected, decreases. For BRAW, the slope is much smaller. And this is, again, like I pointed out previously, due to two reasons. First is increased parallelism, and second is better data storage strategies, in some sense, utilized here. At this point, it would be important to look at that all of these things could be done and all these queries could be run using Java in about the same time, but the cost of writing those queries will be much greater compared to what we are providing here. So some concrete examples for numbers. We see the improvement. For larger size, you see from 30 seconds to 33 seconds to 41 seconds, not very much increase in the amount of time it takes to process. Whereas for Java, you see 79 to 692 and 6,000 seconds. So, and at this point, it sort of becomes fairly difficult to wait that much to compute answer to questions like this. Okay. Next thing we did was we said, okay, can we, if we throw more infrastructure at it, is going to work so for that we scale to more cores. So this shows different charts are for these maps here essentially represent the amount of resources that were available to it. 32 maps essentially means 32 cores were available to it. This shows that as we throw more machine at it, the performance actually decreases. Performance increases, the time taken decreases. So if we continue to add more, we'll see similar trends if we have more infrastructure available to it. Okay. So one of the things that one of the goals for BOA is to be able to replicate earlier results, to be able to. And so if you recall, we brought up this paper earlier, which says 2 out of 154 experimental papers were application friendly, and most of them were due to the lack of published data. I mean, it's understandable because there are cases in which you cannot make data available publicly. So prior research results were difficult to reproduce, and our claim is that BOA makes this easier. And to validate this claim, I would like to reproduce something very small for you today to show to give you a taste of what it is like. So what we have done is we have written about 18, 19 questions using BOA. Okay, and we make this available from our examples webpage, and these questions are in many different categories. And one thing we did was we wanted to show what it would be like to publish a result using BOA. Okay, and this is an example. So imagine that this is essentially what the contribution of my research paper, a very small research paper, would be. What I would do is I would say, okay, this is the research question that I'm answering. Here's a program to answer that research question, and I'm using this data set for my results. Okay. So I can take a look at that data set, and this is essentially please don't try to read this. It just shows you the counter projects. What I'm going to try to do, however, is to try to reproduce this result. So trying to reproduce the result essentially involves copying this program here, going to this infrastructure, pasting it there, picking the right data set, and running it. Okay. So for this trivial thing, it will run, it will give you the right answer. But the essence of this is that if with a simple example query and a tag, this infrastructure will allow people to essentially see what you saw in the first place, without having to build the whole thing. So we also did a control experiment where we used the published artifacts from the BOA website and data set used. And here was the result of this, this control study. So in this study, we had folks involved from postdoc stage to an undergrad student who tried to use BOA to reproduce some results. Some of them were experts, some of them were not. And their task was essentially to pick one task out of the 18 that we provide, and try to see if they can reproduce that result. Okay. And most of them were able to really do this in less than 10 minutes. They were able to show the same results that was published earlier. So there are a bunch of work in this, but none provides direct support for mining software repositories. And so I'm going to give you some examples of that. Sawzall is where BOA comes from, similar syntax to BOA, abstract detail of MapReduce. Pig Latin is another example in this category, the declarative syntax similar to SQL. DryadLink is another example of this kind of language, compiles to Dryad framework. There was some work on Sorcerer, which was essentially an SQL database of about 18K projects, which allowed you to do mining software repositories. BOA is more scalable compared to Sorcerer and more fine-grained because it provides you full abstract syntax tree. Okay. There are some commercial products also available. There used to be a Google code search that allowed you to do grep over repositories, but that allowed you to only answer very limited questions, whereas we provide much more information than that. Olo from Black Duck, it gives you a REST API which gives you project metadata, metrics, etc. For some projects, but this is not. We found that it's not as scalable as BOA is. And then there are things like Google Code Search, GitHub, etc. Compared to those, BOA provides more than just textual map. There are ongoing work in several directions. I'm going to identify the directions and tell you a little bit about that. First, we want to support more kinds of repositories here. So we have support for SVN. We want to do Git, Bazaar, etc. And then we want to support more data sets. We'll expand to Google Code, GitHub, Launchpad. This is more of a logistics question than a research question. But for the data set to be really contain millions of projects, it will be important to have some sort of arrangement with these folks. To have their data set in the repository. We want to enable mining of other artifacts, issues, emails, bug reports, other project-related communication, wiki, etc. And then we want to also be able to design some language abstractions. And some of them we have started to look at already. Last but not the least, infrastructure improvements are extremely important. I mean, as we are throwing more data at it, we are really hitting the scale issues, but we have some progress on making some progress on that also. So with that, I will conclude for today. What I have showed you today is a domain-specific language and infrastructure for software repository mining, which essentially has three goals. Wants to be easy to use, efficient, scalable, and allows you to reproduce research results. So if you have any further questions, I will be happy to take them at this point.
So,
yes.
Do you support intermediate results in caching of intermediate results?
So if, let's suppose you have two queries, and you want to, you are talking, no, currently we do not. Currently we do not support intermediate results.
So each query is totally independent. And
that is correct.
If I wanted to define some tables that could be used among multiple queries and stored in the cluster.
At the moment, we don't, like the website that I showed you does not have support for it. But that may not be the case in a month, because I mean there is somebody already working on it. Yeah. So I mean this is, but that's a good question. Thank you, Tom.
So why did you decide to design an external DSL rather than say a DSL embedded in Java that one could call out to other Java methods to whatever build a comma separated list as an output or run a data flow analysis on the AST, something like that?
It was primarily due to the audience that we are targeting. The goal of BAW is to bring this sort of capabilities to people who may not necessarily be expert programmers, and often giving them an assignment in Java compared to giving them this simple feature. We think that it's likely that they will succeed more here than in Java.
So how hard would it be to support something like that? I would assume that most of your infrastructure is independent of that choice.
That is correct. It would not be very difficult to support something like that for expert users. It has an API-like thing available. It would not be difficult at all. It was simply a matter of selecting the right product for the audience that we wanted to target. Okay. Yes, Rob.
So in the examples that you showed, the scripts are kind of running over kind of cleaned up, well schematized data sets. So what do you think about the other 80% of the job, which is starting with the messy raw data and getting it to a clean data set? Is that kind of in scope for your project?
It is. Okay. If you recall from data infrastructure, one of the important things is to replicate the data from this repository over to. And there are many problems that need to be reconciled for that. So, for example, same things don't mean same across repositories, and it is certainly within the scope. So we have started off with addressing issues related to SourceForge at the moment. Currently, there's a work in progress for trying to see how ontologies for source code matches with ontologies for Google code. So yes, that is within scope. It is essentially an ontology mapping problem.
I was going to suggest that whatever approach you take, you kind of want to make it open, because as more and more miners go after this data, they're going to want to schematize it in different ways to answer different questions. And so if too many decisions get baked into the tool, then that'll hurt adoption, right? So you want to have it pretty open.
Correct. Yes. And at this point, I sort of also want to bring up this another philosophy that we have, which is to not provide interpretation of data, but rather provide the data itself, and let people make their own interpretation, in some sense. Okay. Oh, okay. All right. That's good. Thank you.